Greetings, this is Rob, Chief Flight Instructor for VATSTAR.com, and in this lesson we'll discover a Symphony of Instruments. Now, to keep the video at a reasonable length, I'm going to go through it kind of quickly, so pause and rewind as you need to, and if you still have questions, my contact information will appear at the very end. Let's start with a few vocabulary words. Gyroscope. Well, that's a weighted wheel that's spun at a high speed, which, if you remember from tops or other toys you had as a kid, resists a change in orientation. It wants to stay oriented in the same direction. That makes it useful for certain aircraft instruments, which show the aircraft's position and direction as it rotates around on all three axes. But we'll talk more about those in a bit. Next, knot. That's not like in a rope, although it's the same word. It's a unit of speed that means 1 nautical mile per hour. Those are used in boating, hence the term nautical mile, but it's one of many things that the aviation tradition borrows from the maritime tradition. A nautical mile is about 15% longer than a regular statute mile, so if you're in a plane going 50 knots, you're going 15% faster than a car going 50 miles an hour. There is a reason, by the way, that knots are more practical than miles per hour for maritime and aviation, and that is that they translate more easily into latitude and longitude. But we won't actually get into that in more detail until the oceanic rating. Anyway, where was I? Oh yeah. Speaking of the ocean, mean sea level is the average height of the ocean around the Earth. When we talk about altitude, we usually refer to it in terms of altitude above mean sea level, because that's a baseline average for zero altitude that applies no matter where you are on the globe. Ground elevation, on the other hand, changes depending on where you are, from places that are near or sometimes even below sea level to other places where the ground is hundreds or even thousands of feet up. Altitude in terms of mean sea level gives us a common language no matter where we took off from. Barometric pressure, that's the air pressure of the atmosphere, and the thingamabob you measure that with is called a barometer. You may remember this from grade school science class. The standard unit of measure in the U.S. is inches of mercury, as in how many inches does the air pressure push the little line of mercury up the scale, and the usual range is around 28 to around 31. In Europe and in other places around the globe, barometric pressure is referred to in hectopascals, also called millibars, and the range translates to between 950 to 1050. Barometric pressure is a weather-related phenomenon that can vary from place to place, day to day, and sometimes hour to hour, and its implications on aviation is something we'll get into a bit later in this lesson. Now, before we get into our Symphony of Instruments, let's talk about the pilot's priorities. This is something you'll hear in pretty much any repeatable flight school. A pilot has 3 main priorities, and they're always, always, always in this order: aviate, navigate, and communicate. Aviate. First and foremost, make sure the plane isn't going to fall out of the sky. Well, duh, that sounds kind of obvious. But when you're alone in the cockpit and the visibility is near zero and you're buried in your aviation chart trying to figure out where you are and the radios are going off with air traffic control trying to talk to you, it's easy to lose sight of the fact that the most important thing to worry about is always maintaining control of the plane and making sure that it will continue to be under your control for the foreseeable future. Navigate. If and only if you have aviate firmly in hand, then you can worry about where you are and where you're pointed, and look at your charts to figure out what airspace you're in and what airspace you might need to avoid. Communicate. If and only if you have a solid grip on the above 2 items, only then will you worry about getting on the radio to answer air traffic control or to communicate your intentions to them or to other nearby pilots. Now, communication is something we're going to cover in great detail in a later lesson, but when we talk about the different instruments and gauges in the cockpit, we're talking about aviating and navigating. And now, our Symphony of Instruments begins. So, aviate. That comes in several parts. There are some primary instruments related to proper aircraft handling, then some secondary ones you use to cross-check and verify what you think is happening or what should be happening, and then a whole host of gauges that you watch in order to look after your engine and make sure you're treating it nicely. You want it to treat you nicely, right? Well, we'll get to that in a few minutes. First, the 3 A's. Attitude, airspeed, and altitude. And here are the 3 gauges that correspond to those items. The attitude indicator, this one on the left, is a representation of your aircraft against the horizon. It tells you how your aircraft is pointed relative to the Earth, like we talked about in the last lesson. It uses a little internal gyroscope to hold it in place while the aircraft pivots around it in any which way. Now, if you can see the horizon, you might wonder why this instrument is so important. The instant that you can't see the horizon, though, you'll immediately understand how vital this gauge really is. But it's also important because it helps us quantify pitch and bank angles. It's marked off in 5-degree increments, nose up and nose down, and the little tick marks across the top notate the bank angle. Here's a little video clip showing how it works. Notice that the aircraft stays in the middle of the gauge and the horizon moves around it, tilting to the side for bank, sliding up and down for pitch. Notice the arrow up top pointing to the bank angle marks, and then see how the center of the plane touches these horizontal lines that represents degrees of pitch as it goes up 5, then 10, then 15 degrees. Since banking or pitching too steeply can cause you to lose control or stall, you can see how important this gauge is for safe flying. We're going to skip airspeed for just a moment, and we'll come back to it. There's an important concept about altitude and air density that I want to touch on first. So the gauge that shows your altitude is called the altimeter. Think altitude meter. That's where the word comes from, altimeter. It works essentially like a clock. The big hand is feet in hundreds, the little hand is feet in thousands, and the long thin hand is feet in tens of thousands. Some of them have just one hand and a rolling digit readout like the odometer in an older car, but you get the idea. The first important note is that it shows your height above mean sea level, which may or may not correspond to your height above the ground. In most cases, it doesn't, since the ground elevation at any given location can be anywhere from a few hundred feet below sea level to hundreds or thousands of feet above it, and it changes constantly. Think of when you're driving and how often you're going up or down a hill. I guess some parts of the world are relatively flat, but in a lot of places, the ground elevation is constantly changing as you move around. So for that reason, it's good that all pilots tend to refer to their altitude in terms of mean sea level, so that regardless of where they took off from, they're talking in common terms so they can better avoid colliding with each other. The other thing is, altimeters work by measuring outside air pressure. See, the higher you go, the less dense the air is, and the less pressure it exerts on everything around it. Since that change in pressure happens at a predictable rate, you can determine your height above sea level by measuring the outside pressure. That's how the gauge works, and how altimeters have worked since before there was such a thing as a radio wave you could bounce off the ground and measure your height above it. But because the ground height is changing so constantly as you move around, like I just said, it just makes more sense to talk about your altitude above mean sea level most of the time anyway. Now, here's the catch. Barometric pressure isn't constant. It changes with the weather. Remember high pressure systems and low pressure systems that the weather reporters are constantly talking about? That's what they're referring to, changes in barometric pressure. Since that affects the reading on the altimeter, you have to set the gauge to the local reading to have it read accurately. This is referred to as the altimeter setting, and it's given in terms of inches of mercury or millibars depending on where in the world you are, and your altimeter gauge should show its current calibration setting right on the face of it somewhere. In this example, the altimeter is set to 31.26, a very high pressure day. Now, the actual reading at the ground station is adjusted based on its height above sea level before it's reported to pilots as the local setting, but we'll get into that in more detail in later ratings. Let's take a look at this in action. In this clip, I'm parked at Toledo Executive Airport, which is a smallish regional airport located southeast of the city of Toledo, Ohio, USA. In case you want to look it up, its ICAO code is KTDZ, Kilo Tango Delta Zulu. You can see that it sits a few hundred feet above sea level. My altimeter is reading about 445 feet right now. But wait, the chart for the airport says the ground elevation is 623 feet. What's going on here? The answer is the local barometric pressure is higher than the standard setting of 29.92 inches. Today, the reported altimeter setting here is 30.10 inches. Now you can see that the altimeter is in fact reading the correct ground elevation of 623 feet. As you can probably guess, failing to keep your altimeter set to the correct local setting can cause errors of several hundred or even several thousand feet. And when you're using altitude as a means of avoiding foggy mountains or other aircraft headed towards you at high speed, you can probably guess how important it is to keep that gauge set properly. So now let's go back to airspeed. This gauge is simply titled the Airspeed Indicator, and it too gets its reading by measuring outside air pressure. But its reading is from a forward-facing tube called the pitot tube, and the faster the plane travels, the more force the air entering the tube will have. Measuring that force gives you your airspeed. On some airspeed gauges, like this one, colored bands around the edge tell you what range of speeds are safe for flaps extension, what ranges are safe to cruise in, what speed the aircraft stalls at, etc. So knowing your airspeed and where it falls in these ranges is critical for safe aircraft handling. Now here's the catch with this one. Remember what I just said about how the air density gets lower as you go higher? One side effect of this is that the higher you go, the more your airspeed indicator will underreport your true airspeed. In fact, for every 1,000 feet more you go up, the margin between the indicated versus the true airspeed gets wider by another 2%. By the time you get to 10,000 feet, your gauge might be indicating 250 knots, but you're really going to be making 300 knots through the air. Now, I can hear you asking, why don't we just use GPS to see how fast we're going? Well, 3 reasons. First, aviation is well over a century old. GPS has only been commercially available for about the last 30 years and widely used for about the last 20. Second, airspeed and ground speed aren't the same thing. GPS measures your speed across the ground, but because the air moves, that speed isn't the same as your speed through the air. If you're traveling due east, for example, and your GPS says you're doing 200 knots, you might think you're well above the stall speed. But if you're in an 80-knot tailwind, your speed through the air is only 120 knots, and you could be about to fall out of the sky. Third, and most importantly, the wings of the airplane experience the same decrease in lift performance that you're seeing in the airspeed indication. So your stall speed remains constant in terms of the indicated airspeed as you go higher, even though your actual airspeed at the stall point is faster at higher altitudes than at lower ones. If your aircraft is in its regular configuration and it stalls at 110 knots indicated, that's true whether it's at 50 feet altitude and really doing 110 knots, or whether it's at 14,000 feet and really going 141 knots. So in summary, the indicated airspeed is the most critical measure of aircraft performance when it comes to keeping the aircraft within safe handling limits. So that's what we use. Now, when it comes to aviating, there's also some secondary instruments you look at. These aren't considered primary to fly by because they react to changes rather than changing instantly. So you'll usually change your aircraft's bank, pitch, and power settings using the 3 gauges I mentioned already, and then look at these to verify that your changes are having the desired effect. First, the vertical speed indicator. This gauge is almost always found immediately below your altimeter, and if it points straight off to the left, that indicates level flight, neither climbing nor descending. If you're gaining altitude, it'll point above that, and vice versa. In single-engine piston planes, the scale is usually similar to what's shown here, where the numbers are in hundreds of feet, and the typical range is anywhere from 300 to 1,000 feet per minute. In turboprops and jets, you'll typically see the numbers representing thousands of feet rather than hundreds, with 1,000 to 2,000 feet per minute being typical most of the time, though maybe a bit more immediately after takeoff. The big issue with this gauge is that it tends to lag a couple seconds behind what's happening in this instant. It has 2 little air chambers inside it, and it operates by registering the speed at which the pressure is changing within them. When you change pitch, it takes a little bit for the pressure change to stabilize and settle into a constant reading. So usually, you'll set a specific pitch using the attitude indicator and a specific power setting, which we'll talk about in a minute. Then you'll look at this gauge to see whether the result is as you expected. Another thing is that the climb rate is dependent upon your payload, that is, how heavy your plane is. So the result that you get at a given pitch and power setting is going to vary based on how much weight you're carrying at that moment. Next is the turn rate indicator. That's the top half of this gauge over here with a little tilted airplane in it, and it tells you how quickly your heading is changing. The little marks indicate a standard rate turn, which is 3 degrees per second, but we'll talk more about that in a later lesson. Note, though, that it's not telling you how banked you are. That, of course, is shown by the attitude indicator. This one shows how quickly you're turning on the yaw axis. Now, the idea is that this gauge should more or less mimic the bank angle of the plane, but it doesn't always. As an example of that, watch what it does when you're turning on the ground. It's on the lower left. And see, the little plane icon is going to tilt over because we're changing heading, even though the plane itself is still wings level, which obviously we're on the ground, but it's verified by the attitude indicator up in the center. So be sure you understand the difference between what the 2 gauges are showing. Below that is the slip skate indicator, and yes, it's literally just a little marble that sits in a curved track, so most of the time it's sitting right in the middle there. When it's centered, it's indicating a lack of lateral g-forces. Gravity is pulling straight down. You may have noticed in the last clip that it was sliding back and forth as we turned on the ground. I'm not going to go back to that right now because we're going to cover that in more detail later on. But that's normal because just like in a car, when we turn left, inertia pulls our body toward the right-hand door and vice versa. Well, on the ground, that's fine, but in the air, we want to minimize the lateral g-forces in the cockpit even when we're turning. We want the sensation of gravity to remain centered so we're being pulled straight down into our seat even when the plane is banked to one side. It's not just a comfort thing, it's a safety thing. But like I said, we'll talk more about that in a later lesson. For now, just understand what the gauge is showing you. Now, as I mentioned before, the other part of aviating, making sure your plane's not about to fall out of the sky, is taking care of the engine, making sure the plane will continue to fly in a controlled manner. Probably the number one thing you need to check on in that regard is the fuel capacity. The gauge looks different in every aircraft, and in some it's displayed in gallons, and a lot of others it's displayed in pounds of fuel. The key thing to take note of, though, is that you almost always have more than one tank. Like we said in the lesson on weight and balance, monitoring and managing the fuel consumption and keeping the plane balanced, and making sure that you're not about to run dry, is critical for continued safe flight. We'll get more into fuel planning in a later lesson as well, but for now, just know that you need to periodically check on your fuel situation. The next set of gauges have to do with the engine's performance. Exactly which gauges you see in your plane will depend on which type of propulsion you have, and even still might vary a little bit between one aircraft and another. The example here happens to be from a turboprop plane. Notice the main power setting on the upper left is measured in terms of engine torque. Remember, that's like how much twisting force it's generating. In most single-engine piston planes, your main power gauge is RPMs, but in some larger radial engines, you set power by the manifold pressure, which is how much pressure the fuel combustion is exerting on the interior ductwork of the engine. In jet engines, it's often N1, which is a figure that's a percentage of its rotation speed, but some jet manufacturers have you set power by referencing EPR, which is engine pressure ratio. That's kind of like a comparison of the pressure in one part of the engine to another part. The long and short is that each engine is different, and in each plane you fly, you need to know what power settings are typical for that plane and which gauge you should be looking at to set it. The rest of the engine gauges measure things like oil pressure, oil temperature, exhaust temperature, etc. Exhaust temp will come into play with piston engines at higher altitudes, and we'll delve into that in more detail in a later lesson. For the rest of these, though, the good news is that they'll all pretty much have a green range. That is, they'll have a mark on the gauge that tells you what the normal reading is, so it's usually sufficient to scan them and make sure everything's pointed into the green. Anyway, moving on. Navigation. Now, navigating via instruments is something that we're going to get into in great detail once we get into the P4 rating. For the P2, we really only need to understand the basics of what the gauges are telling us. The main one we use in most planes is called an HSI, which stands for Horizontal Situation Indicator, but that shows us quite a lot of information, so we're going to start simple and work our way there. The simplest navigation gauge is the heading indicator. Now, you might look at that and say, oh yeah, a compass. I know what that is. Well, yes and no. Yes, in the regard that it's showing you a heading in degrees, and we usually call that a compass heading, and yes, it's usually aligned to magnetic heading, so it's the same heading that the compass is showing you. But this gauge is gyroscopic. That ensures that it reacts to heading changes instantly and precisely. The magnetic compass is much more prone to bobbing and floating around and doesn't usually settle into a new heading reading until after several seconds of steadiness. The compass in most simulated planes actually is way more precise and easy to read than real ones, which get jostled around quite easily. So the wet compass is there as a backup, but the gyroscopic heading indicator is much more reliable for an instant read on your current heading. Next is a VOR gauge. This is used in navigation methods which are based on radio beacons that you tune on your nav radios, and the needle shows a left or right deflection based on where you are in relation to the course that's set on the gauge or within the station that you've tuned. This particular example also has a needle for vertical deviation, so you can use it to track a specified lateral course plus a vertical descent path for a radio-based landing approach called an ILS, or Instrument Landing System. VOR stands, by the way, for VHF Omnidirectional Range, but we're going to get into all that in a later lesson, so for now, just know in broad terms what the gauge does. Finally, the Horizontal Situation Indicator, or HSI, as I referenced before. This is a gauge which combines a gyroscopic heading indicator with information on the VOR gauge, including, in most cases, the vertical guidance information. The plane's actual heading is straight up. The course that's set on the VOR portion is shown via the yellow arrow. The displaced portion of the arrow shows the course deviation to the left or right of that, and the pointers along the left and right edges show the vertical guidance for instrument landing approaches. At the bottom, the knob with the arrow adjusts the desired course. The other knob sets the heading bug, which is basically just a reference heading. Usually if you have the autopilot set in heading mode, that's the heading it will try to fly the plane in. But the bug can also be set as just a visual cue for the pilot, such as a heading that you need to turn to momentarily, or the pilot or the autopilot might be trying to track the course arrow, which means it'll ignore the heading bug completely. One more piece of navigation equipment that most aircraft carry is called DME, or Distance Measuring Equipment. It takes a radio signal from a navigation beacon and determines the straight line distance between the transmitter and the receiver, and it displays that distance in nautical miles. Most DME displays have a selection switch so they can show the distance associated with either the station tuned on Nav 1 or Nav 2. In addition to the distance, most DME boxes also show the closing speed in knots, meaning the rate at which you're getting closer to or further from the station. That's not necessarily the same as your ground speed, although it's pretty darn close if you happen to be headed directly toward or directly away from the station in question. If you're headed at an angle, the speed is going to show lower than what you're actually traveling. A few DME units, such as the one in this example, also show the ETA to reaching the station in minutes. Again, that's only accurate and applicable if you're tracking directly toward it. But it's a simple time distance calculation based on the other two values right there on the display, which saves you a little math when you're checking your flight progress against your original plan. One thing to keep in mind is that not all VORs and ILSs transmit DME signals, so if you're tracking a radio beacon and you're not getting a DME reading, it might not be a malfunction. The chart with the station's frequency probably tells you whether it's DME capable. Again, these are things that we'll get into in more detail in the P3 and P4 ratings. So, let's quickly summarize the key points. Aviate, navigate, communicate. Aviate means flying your plane in a safe, controlled manner, paying attention to your attitude, your airspeed, and your altitude, and cross-checking vertical speed, turn rate, and slip and skid to be sure you're keeping the aircraft under control. It also includes keeping tabs on your available fuel and ensuring you're treating the engine with due care and looking out for signs of any pending problems. And navigate means combining information about your heading with information about your position from radio navigation stations, plus DME information, so you can determine where you are and where you're going. Got it? Good. If you have any questions, shoot them over to me in an email at cfi@vatstar.com. We'll see you in the skies.